chain rule. So like this is a, my answer is allegedly this. So my point is if you differentiate this, you get 1 over that thing squared, but you also get a minus because it's the -1 power, and that's what we have.
Okay, yeah.
So I think I'm okay. And then we got what? We got, I'll leave the KQ over A out front. I'm not sure that trick I did with the minus really matters. A minus R minus A. We should get the same answer if you didn't do it, you know? We can clean this up. The A's, they be canceling. Yeah? And so what we got here is a KQ over A times 1 over R. The minuses also cancel. And then minus 1 over R plus A. Let's make a common denominator here. This is the part I was hurrying in class, and that was at the end of class, so my bad. I'll try to go a little bit slower in class, generally speaking, as we go on. I think we've got time for me to like, the pace I went today is the pace I'd like to keep at. Like I was going a little bit too fast, I think, at the start of the week. Anyway, so just made a common denominator, you know. And you know what happens here? The R's, they be canceling. And then we can reduce the A's as well, because it just leaves you with A over A, which gives you a net of KQ. Yeah, over exactly R times R plus A. And since this is an odd problem, we will now have the satisfaction of checking the answer. I'm gonna try anyway. The answers are like way in the back. I don't know. You have to go like, I don't know how to get that in your electronic book. 21. This is 21. What was it?
79.
79. 21. 79. Oh man. Wait, what? I'm confused. They got it in terms of x's. Did I copy the problem down wrong? Where'd it go?
I was like, I feel like that wouldn't make sense because you're integrating it in terms of x.
That's weird. I think there might be a typo on the key. Not cool. Well, I could be misreading the problem, I guess, but they didn't simplify their answer. What the? Come on, guys. Seriously? Lame. Not impressed. Not impressed. Well, it says right there, it says in part C, show that if R is much, much greater than A, then the magnitude of the force in B is approximately QQ over 4 pi epsilon R squared. Explain why this result's obtained. So yeah, let me not fuss too much about the answer in the book, because I think they've got a typo or something there for the answer to 79.
I was like, the
X.
thing would make sense over.
Oh, right, yeah. Oh, right. So if R is much, much greater than A, in other words, if the size of the rod is small compared to the distance away from it that you are, it's essentially, this is just KQ over R squared, which is the Coulomb field. It's as if it's just a point charge and it's not spread out. This is the kind of phenomena we should see for any point charge. Now, if you've got like a charge and another charge and a negative charge, like with the dipole problem, it doesn't have to be the case that you get a Coulomb field far away. Or like today we saw that for a charge, for the positive charge and the negative charge put together, we had the epsilon over sigma over epsilon naught between the planes, but outside of the planes, the field was actually 0. So like this limiting to the Coulomb field, it should only happen for like a charge distribution that's like this. Or I can be more, actually next week we're going to talk about Gauss's law. I'll be able to make that fuzzy idea I'm giving you much more precise. So
How would it change if the line was upwards in the y direction, and then the test charge was still to the side?
wait, what?
How would it change if the line was upwards in the y direction and q was still sideways?
Oh yeah, we could look at that. Let's see here. So if I can find a here. Can I erase all this? I think, yeah. Actually, I'm going to leave this because that way we can contrast. Do it over here. Let me set it up for like a really ugly point and show you why we're not going to do that. Why we won't actually do the calculation, you know? So suppose we had charge that's distributed, say, from like L to minus L, something like that, right? And so here's the origin. So I've got a charge Q uniformly distributed like that. Suppose I want to find the electric field here. What's the electric field here?
Where y and x could both be anything?
Yeah, well, for the sake of specificity, let's suppose that x and y are, let's suppose x is positive. If we do the equations right, it'll actually take care of other cases. Like we can basically fall back on the formulas that I shared with you guys at the start of this week to set this one up. We're not actually I don't think we can do the calculus here after we get it set up, but it might be instructive to see why I don't ask this question. You know? Although there was a year I asked the physics 2 to find the electric field due to like an L of charge, and I put the point at like on the diagonal, but then they like refused to do it. So I don't know. I don't know what that means. Yeah.
Would it not be like a lot easier if you had an example where y was like 0? Because then everything going upwards, everything going downwards would.
Oh yeah. If y equals to 0, then it's nicer.
Then it's just trying to see the x components.
Exactly. So if we put dq here, right? And we can say that that's at y. Well, it's at 0 y, right? Then we just need to figure out what's the distance, you see. Well, really, we just need to find the displacement vector from there to there, which it's going to be xy minus this point, which is 0 y. Oh, my bad. This is why I can't do this. I am conflating two things. The y here and the y there. I didn't mean to make those the same y. I can't do that. I need a variable over here for integration. I should use something else like little l perhaps, or I'll use a little l for that, for a variable. So like minus l is less than or equal to little l is less than or equal to l. So that I'm going to end up doing an integration over little l as I currently have it set up. So I should have said this minus that. So then the displacement vector from there to there would be x comma y minus l. And that's not a unit vector, that's just the displacement. So the infinitesimal electric field from that little bit of charge what would it be? Well, it would be k dq over, and so we could do, I'll write it this way to start with, okay? But a more convenient formula will be as follows. My dq is really nothing more than dl times q, it's q dl divided by what?
L squared.
No. So like, what's the charge density here? Lambda. We're talking about dq, d little l. It's what? The total charge is q, that was given. If it's uniformly distributed, what's this length? What?
Oh, just over.
I just didn't hear you. What'd you say? It's 2L? It's 2L, right? So this one has 2L, so we read 2L here. Earlier today I did 2 pi r because it was all the way around a circle. This one we did L because it was distance L. We have to think about. Anyway, so my dq is q over 2L dl. Now I still got this r squared business, but what I'm going to do is I'm going to do like this. I'm going to do x comma y minus L divided by the square root. Well, not even square root. Not even square root. I'm going to do x squared plus y minus L squared, parentheses, to the 3/2 power. This right here is just this formula is just nothing more than this over that. And then to find the net electric field at that point, I just have to integrate this from here to here to add them up. So like the net electric field at the point would simply be, I say simply, but I don't mean to say that actually carrying this calculation out would necessarily be simple. I think it'd actually be far from simple. Integral from minus L to L of x y minus L divided by, x squared plus y minus L quantity squared, all to the 3/2 power. And that's an integral over dl. So this will be a vector. So when you do an integral of a vector like this, we mean the vector of it. Like this is 2 integrals. To be more, if you want me to be explicit. That would be it. So you just have to do those integrals. Yeah.
But if the y was 0, you would just do the first integral and then just have y equal to 0.
So you're like, what special case? What if y is equal to 0? So you're asking, what if the field point is like here?
Yeah.
Right? So in that situation, if you think about, of course, the electric field from this one, there's a corresponding one from down there, right? And you can see from the symmetry of the problem, since it's distributed from minus L to L, that the net electric field there, of course, should be in the x direction. So it must be that if we were to put y equals to 0 in these formulas, it should actually be manifest that this integral is 0.
Yeah.
So if I put y equals to 0, I've got like integral of minus dl 3/2? Huh. I don't know, guys. Not sure I see it right off. Why that integral would be 0 in that case. I mean, it should pop out at me.
Is it not just because the L to 0 is like so common and 0 to negative is the opposite?
Yes, it's exactly that. Thank you. I am thinking about a y integral, but should I be thinking about a y integral? I should be thinking about an L integral here. Notice that in the case y equals to 0, we've got an integral of, check out the formula, L over this stuff. The denominator is an even function of L. The numerator is an odd function of L. Altogether, all told, it's an odd function of L. When you integrate an odd function about a symmetric interval of the origin, it's 0. This is one of the things you should have learned in calculus too. We don't emphasize it much, but it's actually really important for engineering calculus. Integral of an odd function about a symmetric interval of the origin is 0. That's why this is 0, which is just the mathematical reflection of the symmetry we saw in the picture in that special case of y being 0. So if y is 0, this is 0, and this simplifies a bit. It's just integral of x dl over like x squared plus L squared, which is then an integral you can, I think we did that integral today, actually. I think we did that integral today, actually. So, is this a mission problem? This feels very mission-y. But you asked a conceptual question, so you didn't ask me, do mission problem such and so forth, so I'll allow it. You're like, hey, if you don't educate yourself on the problems in your own mission to ward yourself against helping me do the mission, that's your problem. And that's a fair point. Point taken. Let's see here. Any questions? Let's see here. When does this thing end? What time did I say we end at?
20 minutes.
20 minutes. All right, so we got time for another problem. If you guys want me to do one. Let's see here. We could look at number 57. That might be a good problem. I think we've done enough integration for today. Yeah. Let's look at some chargy problems. So just to give you guys a snapshot of like where we're going test-wise, the test covers chapters 21 and 22. 21 is all about what we've been doing. It's like given a charge distribution, find the electric field. And you either do it from taking like the vector sum of the Coulomb fields from a couple point charges, right? Or you have to do some integration like we just did.
Are we near the end of, did we just finish chapter 21?
We're just about there. There's a little, there's a couple, like a page and a half on like torque and a dipole. I haven't done that yet. So I probably should do that at some point, but I might come back to that later. I think I'm likely to go on to chapter 22 Monday.
Okay.
So I don't know, my schedule might say otherwise, but it kind of feels like it's time to go on to Gauss's law at this point. Whatever I missed in chapter 21, I'll probably circle back to and get later. So this is problem 2157, which is on page 740. And here's the deal. Ooh, it's got 3 blue dots. That's scary. 3 blue dots must mean very difficult. I don't know. I really wonder, what do these dots mean? Do you guys have an idea? I don't know. Oh, really? Oh, man, I don't know. We could be in trouble here. We could be in trouble. 3 dots. I don't know. So you got 4 identical charges Q placed at the corners of a square of side L. So you got yourself Q. 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 And, 4 identical charges, Q. Okay, great. A, in a free body diagram, show all of the forces that act on one of the charges. And then B, find the magnitude and direction of the total force exerted on one charge by the other 3 charges. Why this got 3 dots? This is take a candy from a baby. It's not a hard problem. This is a typical test question of mine. Let's see here. That's not a joke, actually. I've given this problem on tests. Or not maybe this exactly, but something very similar to it. So the fundamental idea here is, does a charge put a force on itself? The answer is no. So when we think about the net force on a charge due to other charges, we think about other charges. We don't think about the charge itself. So you pick any which one you like. For the purpose of my artistry, let us pick the lower right one. All right? And let's enumerate these things so that we don't go nuts. 1, 2, 3. And so we're going to find on Q4 here, we're going to find the electric force due to the other two. So the picture, it says, the first part A says, draw a free body diagram. Right, you guys remember those? Yeah. So we've got the force from 1. We've got the force from 3. And we've got the force from 2. And don't read anything into the magnitude of the forces from my arrows. They're just directional. Yeah?
But the force for Q1 and Q3 should be like equal in magnitude, right?
Absolutely. Yeah, I totally agree. Now, it was given to us that this is the square of side length L. So to be clear, this distance here was L, and this distance here was L. I guess the thing that makes this a 3-dot problem is that you have to figure out the distance from here to here is not L. What is it?
The square root
Uh-huh.
the square root of L squared plus L squared.
Square root of L squared plus L squared is correct, also known as L times the square root of 2. Right. So, yeah. All right, I think with that added to the picture, it's now only a 1-dot problem. But I don't know. So what are the formulas for the forces?
What are we trying to find after that?
So the first part was to draw the free body diagram, all the forces on one of the charges due to the other 3. So we did that. Then the next part was to actually find the force. And let's find the acceleration. Well, I shouldn't say, let's just find the force on it. We never really answered the question, how is it that these 4 charges are stuck in space like this? I warned you guys about this day 1. We're just going to stick star charges places and never explain how they got there. This is the nature of this course. Everybody's doing it. It makes it right. So, hey, I talked about a capacitor today. That's real. Right? Yeah. So let's actually find the net force on Q4. Okay? So the net force on Q4 is, I'll call it F net, and it's F1 plus F2 plus F3, right? I know at the start of class I confused you guys a little bit with like my 1, 2, 2, 1 notation. That was for the sake of that discussion, right? When we actually get into the problem, solving problems, a lot of times we just use 1, 2, 3 because it's clear what it means. You know, I don't need 1, 4, 2, 4, 3, 4. I mean, I could do that. But why? So this, let's just write it down. I mean, we got K, Q, Q divided by what? What's the distance? For 1 to 4? L squared. What's the direction? Well, F1, I can write it out, formula here for you, F1 x hat. F2 is more complicated. F3 is, yeah, F3 minus y hat, but yeah. Now, F2, it would be F2 times like, it's a little complicated, but it's 1 over the square root of 2, comma, minus 1 over the square root of 2 is what it is.
So it's like the 45-degree angle?
Right, minus 45 for that one,
Yeah.
but that would be...
Okay.
Now, probably what the book wanted you to do is to like find the x component and find the y component using trigonometry and then add them separately. Like you could do it that way. That's the way I would have done as a student to start with, but what can I tell you? Okay, so here we've got this for that one. F2 is a little bit more complicated, but it's K, Q, Q over L times the square root of 2
Isn't this the
squared.
equation for the electric field?
I'm doing the force because I get QQ.
Uh,
Why is it QQ?
Because it's because the charge, the source of the electric field and the charge which it's acting, they're both equal to Q. All charges are Q here.
okay.
So Q1, Q2 is QQ. I could just write Q squared. Be less weird, but just.
Wait, then,
I'm not finding the electric field, I'm finding the force on Q.
Okay.
So it's Q times the electric field there. Like this would be equal to Q times the electric field at Q4. So I don't know, like this is the way I thought to do it. Again, you could do X components and Y components and then add them together, but I'm just writing that down because I know what direction vectors are and I know that that puts this vector in the right way. And then F3 is, minus KQQ over L squared Y hat. I put the minus up front. Let me put this stuff all together. Let me factor out. We've got a KQ squared over L squared everywhere, right? And if you look at this, we get a 1 from here. And be careful here. So this is 2L squared. So I really get plus 1 over 2 root 2. And then I get a minus 1 from that. And I get a minus 1 over 2 root 2. Listen, this is probably not the way anybody in this class is going to do this calculation. That's fine. This is just how I do the calculation. You can, again, you've got 3 vectors. You find the x, the y components. You add them together. You find the net. Yeah.
this is off topic, but what's the formula for electric field then? Because I thought that was the KQQ over R squared.
Just 1 Q.
Oh yeah.
Just 1 Q.
Okay. So
It's confusing here
that's
because
why I was thinking
it's confusing here because the source charge, and the field charge, they're both big Q. So like
you did the KQ over R squared R hat times the Q that's already in there.
uh-huh.
Okay, that's what I was confused by.
So notice that this is exactly what I don't know if we forecast this or not, but you told me these have equal magnitude, right? So if I was to draw these vectors like in a vector diagram, you can kind of see what's going to happen, right? You got one that goes like this, you got one that goes like this, right? You got one that goes like this. So the net, it should be down at 45 degrees, which is what we see here, same magnitude, right? This is 45 degrees down, and like, let me just rewrite that. That's K Q squared over L squared. I can factor out a 1 plus 1 over 2 root 2, and then I'm going to multiply by the square root of 2, and then put a 1 over root 2 minus 1 over root 2, because then that's a, this is a unit vector, which means whatever I wrote over here has to be the magnitude of this thing.
Okay. You got the 1 plus 1 over 2 root 2 and then the square root 2 just from taking that out of the
Yeah, it's the same number here and here, so I can factor it out. That would leave me 1 minus 1. But I didn't want to leave that because I'm interested in the unit vector. So I divided and multiplied by the square root of 2. And after I do all that, I've got myself a KQ squared over L squared times like what? Root 2 plus apparently 1/2. So there's the magnitude of this bad boy. And it's like that there. But of course, the symmetry of the problem suggests that at any one of the 4 corners, the magnitude of the force from the other 3 would be that,
be the same but with different signs.
pointing away. Let's see what the book says. This was an odd problem, right? I'm not sure. Should I recommend this problem to the class? I feel like any problem I work in here I should recommend, right? That way I don't have to work it again. Ooh. It's got Q squared over 8 pi epsilon naught L squared times 1 plus 2 root 2 away from the center of the square. q squared over 8 pi epsilon naught L squared. Q squared over 8 pi epsilon naught L squared.
And then the k equals like 4 pi epsilon?
Yeah, what was the rest of the answer? I just lost it. Sorry, just a second here. I wish my memory was better. A 1 plus 2 root 2, right? How does that compare to my... So if you take, this is the book's answer, right? If you pull a 2 out of that, you get 2q squared over 8 pi epsilon naught L squared times 1/2 plus the square root of 2, right?
Yeah.
So this is the book's answer. I did one arithmetic step, but what is q squared? But this 2 over 8, notice what we got here. I mean, that's my answer. See this? This is 1 over 4 pi epsilon naught, which is, okay. So I'm telling you these things because if you're working problems and you get an answer in the book that looks different than your answer, this is one of the things you need to think about. Sometimes I guess the book tends to write everything with epsilon naught from what I've seen. But this is one of my, well, unless I say otherwise, you can either write an answer with k or with epsilon naught, you know? That's why they pay me the big bucks, so I have to understand both are correct answers. But if I'm smarter, I will pigeonhole you into the letters you can use in your answer so my grading gets easier. But I'm not that smart. Half the time. I'll tell you what's bad though, is in here later when I give a circuit and I say find current and voltage, and the students, and then it turns out like the circuit's impossible. I've done that. So I've learned that if I write a circuit problem, it's important to include language. If possible, find the current and voltage. See, that's why you should always package physics problems with that, because when you ask questions like we saw today, like there doesn't always have to be an answer. It's possible to phrase a physical problem such it doesn't have an answer, you know? I don't, like, so if you look at the end of the book here, right, like, I mean the end of the chapter, you could literally just spend the rest of the semester solving these problems, right? Like there's so many of them, which is...
Answers.
Did you find them yet?
No.
It should be at the very end of the book. So, the answers to odd numbered questions right there.
Oh, I guess I just
Yeah, it's easy to miss. Now, if it would be more convenient for you to take pictures of mine, so you just had all the problems in like a picture, feel free. Uh-huh. In fact, I might even have like, I think I scanned the book for like Physics 1. I need to find if I don't know, anyway. I haven't scanned the whole book, obviously, that would get you in trouble, but anyway, thanks guys. Your peers should be happy that you came today.